Hello everyone. Today I'm excited to share a geometry problem from a SuMON math program of Fortnite 31. This is a hard problem based on parallelograms in geometry. We need also some prerequisite knowledge to attempt this problem. We will first look into the question, then we will get into the prerequisites. Let's get started. Based on the area ratio of the particular area and the entire area of the parallelogram. Here's the parallelogram. So the vertex B is joined to the midpoint of AD and vertex D is joined to the midpoint of BC. And vertex A to the midpoint of CD, vertex C to the midpoint of AB. Now they all intersect and you will form a nice quadrilateral over here. And in fact, this will be a parallelogram. The reason being that these two lines are formed by joining a vertex to the midpoint of its opposite side. And since they are equally inclined due to the symmetry, they will naturally be parallel. Similar argument goes for the other set of parallel lines, and therefore the formed quadrilateral will have two opposite sides parallel, and hence it is a parallelogram. But they are not asking about the area of the parallelogram. And in fact, we will, as a part of the process, we will find the area of it. But we need to go deep than that. We have to eradicate these two areas defined by joining DP and CP. So after eliminating that, we will get the shaded area of a hexagon labeled with H. So there are some prerequisites, namely Menelaus theorem and some area ratios. We will first look into Menelaus theorem. Menelaus theorem states the condition for the 3 points on sides of a triangle so that they are collinear. So diagrammatically speaking, consider a triangle, label the vertices ABC. Of course, you must have at least one of the points on the sides lying external. Maybe all three lie external. So as you could see, we have one point external to the side BC and two other points internal to the sides AB and AC. So the point on the side BC, call it D, on AB, call it F, and on AC, call it E. So you have DEF collinear, and we need to impose some constraint on the positions of these points so that they are collinear, right? And the condition follows like BD upon DC times CE upon EA times AF upon FB equal 1. If this is true, then the 3 points are collinear, and if the 3 points are collinear, this must be true. Let's remember this, and also the ratios are not signed. Alright, this is true for any triangle. Now going to area ratios, we need some basic notion of area ratios. So consider a triangle, and if a CVN joining a vertex dissects the opposite segment at D, then BD by CD denotes the area ratio of ABD to ACD. This is due to the fact that they share a common height and they share a common baseline. So eventually the half into base into height will not have the half into height in their area ratio. So we will end up with the base ratio. Using these two, let's attack the problem. Majorly the given configuration has the following. You have ABCD, I think that's how they are oriented, and B is joined to the midpoint of side AD, call it as BS is extended to intersect the side CD at a point, say T. Since S is the midpoint, you have AS equal SD, and these two angles are equal, and these two angles are also equal as AB is parallel to the line CD. By ASA congruence, the triangles ABS is congruent to triangle DTS. And therefore, notice that DT equals AB, but AB in turn equals CD because opposite sides of a parallelogram are equal in length. And now let's consider the segment CP and DP where P is the midpoint of AB. You will get something like this. AP equal BP. Let BS intersect CP at R and maybe not R, let's call it as X, and DP at Y. Consider Menelaus in triangle Menelaus in triangle DPC. Let's take a closer look. Notice that x, y and t are collinear points on the sides of triangle DPC. We assume that t, though external, lies on the line CD. Therefore, you get dt by tc times cx by xp times py by yd equal 1. Notice that both dt and cd are of equal length. So, dt by tc will be 1 by 2. So, we get 1 by 2 times cx by xp times py by yd equal 1. So, let us find cx by xp now. Observe that in triangle ADP, the points S, Y and B are collinear. This helps us in finding py by yd. Let's do that. So, Menelaus in triangle ADP would give us AS by SD times BY by YP times PB by BA equals 1, and AS equal SD, so it's 1 times dy by yp times pb equal ap, and therefore pb by ba will be 1 upon 2 equal 1. So, from here we derive that py by dy equal 1 by 2. So, in other words, if pd is of length L, then py is of length L by 3 and yd is of length 2L by 3. So, 1/3 and 2/3. Alright. For now, let's erase dy, we will not require anymore. Substituting it back in the first equation that we got, we get half into cx by xp times py by yd, which is 1 by 2. And that's 1. And this renders cx by xp equal 4. Well, if I consider Cp length as t, then Px is going to be t by 4 and Cx will be 4t by 5. So, Px will be t by 5 and Cx will be 4t by 5. Therefore, we get 1:4 ratio. Alright, now we compare the areas of DPC with the entire parallelogram. Notice that DPC and the entire parallelogram share the common height, which is the perpendicular from P onto the opposite side CD. And they also share a common base, that is CD. And hence the area ratio is just half, because area of a triangle is half into base into height, whereas a parallelogram is base into height. So, area of DPC equal A upon 2. I consider A as the entire parallelogram's area. Now, notice that it can also be written as half into LT sine theta, which is where theta is the angle between DP and CP. So, this is a common well-known area formula, that is half into product of adjacent side times the sine of angle included between them. And that's what I have expressed. L is PD and T is PC. Now, area of PYX will be, by the same logic, half into L by 3 into T by 5 into sine theta, because the angle is same. This renders the area is A by 2 upon 15, therefore it is A by 30. So, we get area of PYX to be A by 30. Let's also shade that for more clarity. Okay, now we are going to join the vertex A to the midpoint of CD. Midpoint of CD is labeled with R, and if you join A with R, you would observe that AP equal DR, because both of them are half of two equal sides and they are also parallel. Therefore, APRD is a parallelogram, and hence their diagonals bisect each other. And now we got something interesting. This length is just L by 2. Let's name it with something, maybe Z. So, PZ is L by 2. Therefore, YZ will be L by 2 minus L by 3, because PY is L by 3, which makes it L by 6. YZ is L by 6. Notice that if we consider the intersection of BS with AR as W, then triangle, the smaller triangle WYZ is similar to PYX. WYZ is similar to PYX. This is due to the fact that it is subtended by two parallel lines with two transversal PZ and XW. PZ and XW. So if you have any two triangles subtended by parallel lines, then you are going to have them similar, because this equal this, and basically the alternate interior angles are equal, and therefore the triangles are similar. So let's write down the similarity. We get that triangle WYZ is similar to triangle XYP. Now notice that the area ratio will be square of the corresponding side ratio. The corresponding side ratio is YZ upon YP, right? That is L by 6 over L by 3, which is 1 by 2. Therefore, the area ratio will be 1 by 2 whole squared when you have WYZ upon XYP. Therefore, we have area of WYZ upon XYP equal 1 by 2 the whole square. This makes area of WYZ equal XYP. XYP's area is A upon 30. That's what we proved here, the purple shaded area. So it would be A by 30 times 1 by 4. This means that the area of WYZ is A upon 120. Now let's get back to the original diagram and you will be able to relate everything. So here is our original diagram, and we have W here, Y here, Z here, and this area is A upon 120, and this area is A upon 120. So we just need to find this parallelogram's area and subtract twice of A upon 120 and we would be done. Now let's find the parallelogram's area. Notice that by let's call this point as X. This point is X. Notice that PX is half of AW by the midpoint theorem in triangle ABW. PX is half of AW, and also it is parallel. So therefore, if I reflect X upon P, I would get X prime. And if I join X prime to X, it would be equal, as it is double the length, and it will also be parallel, therefore forming a parallelogram. So A X prime X W is a parallelogram. Now these two triangles A X prime P, so you should note that this is X prime, not X. This triangle is congruent to BXP. This is just by angle, side angle congruence, due to which this just looks like a rotation of triangle BXP about P. So just cut it out and dissect to rotate about P so that BP falls onto AP and both of them overlaps. So this forms a entire parallelogram that is congruent to this parallelogram. This is due to the same side and the same angles. So they will definitely form congruent parallelograms. And similarly, you rotate this one and you form a parallelogram here. You rotate this one about R and you form a parallelogram here. You rotate this one about S, you form a parallelogram here. And these areas will now be not present. So I'm just shading it, which in essence is eradicating it. You should observe the diagram now. It's quite noticeable that these four parallelograms along with the middle one dissect the entire area into 5 equal parts as they are congruent to each other. And hence, the area of the middle parallelogram is just A upon 5 because the entire area is capital A and it is divided into 5 equal parts. So the required area will be obtained after subtracting twice of A upon 120, and that is 12A by 60 minus A by 60, which is 11A by 60. And therefore, the area ratio of a required hexagon shaded in red to the entire area of parallelogram will be 11 by 60. So it's 11 parts of total 60 parts of the parallelogram. So we solved some interesting problems and geometry constructions like this in our worksheets. We provide 8 problems in each of our worksheets. So stay tuned to learn more. Bye.